Okay, sorry about that. So, can we- so we start the afternoon session with a talk by Manoel Silva de Vasconcelos, here from the Federal University of Rio Grande do Norte. And he's going to be talking about Plasmon-Polaritons in semiconductor photonic crystals with graphene.
Okay. Um, I'd like to thank the organizer for inviting me to contribute with this talk. And I'd like to thank Felipe. Felipe personally invited me and to give this contribution. I'm very glad to be here. I will talk about Plasmon-Polaritons semiconductor photon crystal with graphene. This work was done during my sabbatical year in the Western Ontario in London, Canada, and this work was done together. Michael J. Cotton is one of my collaborators, and sorry. Here is where I work. I don't work on Department of Physics, but I work in the School of Science and Technology. This is 10 years old the school. This is close to here, around, is a walk distance. You can spend 11 minutes walking, or 13 minutes by car. Okay, this is outline of my presentation. I'll introduce why I will study this kind of system, and I will talk about photonic crystals and polariton and Plasmon-Polaritons with graphene. Of course, in the past week we have a very nice talk about this kind of subject that was done by Nuno Paris, but I will just to recover some kind of characteristic like dispersion relation Plasmon-Polaritons, and I will talk after I talk about the theory that I will use to describe the Plasmon-Polaritons in semiconductors photonic crystals, and I will finish with the conclusions. Okay. Here's this picture is just to show that today have a big area they call metamaterials. Some people search metamaterials, and some people define metamaterials like a man-made materials. Okay, that you can construct this material for one kind of application that you want. For example, optical. If you choose optical application, you have in this big area a photonic crystal. Obviously, historically, the photonic crystal was developed first. Okay, and this talk I will focus on one dimension or 1D photonic crystal. Of course, that others that had others kind of photonic crystal. The definition of photonic crystal is very simple. When we have periodic arrangement of dielectric materials or metamaterials, and that exhibit a strong interaction with the light. Why the scientists and the engineer is interested in the photonic crystal? Essentially, is due to this kind of material have band gaps, like band gaps in semiconductor for electrons in semiconductor, and you can construct some device, for example, one kind of transistor using the light as in the place of the electrons. Okay, this is essentially the motivation. This kind of thing can change all the technology about transistors. Here are some examples of photon crystals. You have a Bragg reflector. This is essentially if you have a multi-layer of dielectric periodic arrangement of the dielectric layers, you have one kind of this system will behave like a mirror that will reflect, depend on if you have frequency in the band gaps or if you have the frequency outside of the band gap. If you have in the band gap, this light will reflect totally in this kind of system. Here is there are other examples like 3D colloidal crystals. Let's go. This is this picture. We have a kind of a series of applications. You have, for example, negative index imaging. We have optical fiber. We have resonant filters, or so on. This is just to give improve in my talk to give some applications, to give some idea how I can apply this kind of system that I will talk about. Now I will introduce you to polaritons and Plasmon-Polaritons with graphene. Okay. Generally, the term polaritons refers to a mixed mode when you have one of the components is essentially the light. The other is a dipole active elementary excitation, like phonons, plasmons, magnons, excitons, etc. And this mixed mode is a coupled mode between phonon and this kind of dipole active elemental excitation. The basic properties of the polariton may be obtained using a function, dielectric function, or a frequency-dependent dielectric function, for example, for optical and magnetic characteristics of your system. If you have this frequency-dependent dielectric function, you can, for example, in the approach that I will do, you can use the Maxwell equation to describe the polariton. Of course, there are other kind of approach like quantum. You can write a Hamiltonian when you have a coupling between photons, or a part of the Hamiltonian will have a photon. The part of this Hamiltonian will describe the photon. The other part will describe the excitation, and other part you have coupling between this excitation. Okay, but here I will show this approach. I will talk about this approach using Maxwell equation. The K of this approach is in the, for example, for Plasmon-Polaritons, you will have this vector that is one of constitutive parameter of the medium. The displacement, the electric displacement of the medium is related to the electric field by the dielectric function. Okay, Of course, other kind of the consideration is a kind of ansatz that you can not necessarily you can use this, but you can consider a plane wave propagation like a solution of this electric field, and this this Maxwell equation, and you can, for example, you can obtain the polaritons for Plasmon-Polaritons behavior for the answer for the plasmons. Here, if you use the answer for the dielectric gas, two-dimensional electric gas in the 3D medium or a continuum medium, you have this kind of answer. This is a dispersion relation when you have part of this curve, we have a behavior like a plasmon. This is a frequency of the plasmons, and this is the light line. And you have part of this wave. We have behavior like when you have omega. If omega goes to infinite, here you have a straight line. This is essentially that we have for the behavior of the Plasmon-Polaritons if you have a bulk or a continuum medium. If you consider interface between two mediums, okay, this is the dispersion relation you can use. This dispersion relation is obtained when you apply the Maxwell boundary condition between these mediums. And the answer is that this is a dispersion relation. You can find this exercise for undergraduate course. So it's one kind of exercise that you can do for solid state physics, for example. Or introduction to solid state physics. And then we have, this is the bulk mode. This is the same mode that I had showed before here. Sorry. This is the same, like a parabola behavior. And you have, sorry. When you consider interface between two mediums, one of these mediums is called active medium. We have this surface mode. This surface mode will propagate in this direction, in the direction parallel to the interface between this medium, and you have this kind of dispersion relation. For low frequency, we have a behavior like line, and for more high frequency, we have a behavior like a plasmons. Okay, this is a mixed behavior where you have in this case. But if you put the graphene between a graphene sheet deposited between this medium at the interface, you have a new behavior. This is one picture that probably was showed for Professor Nono Perez. This is from one reference of Professor Nono. And then here we have essentially the same kind of behavior of you have a single interface between two mediums. Of course, if you want to calculate the Plasmon-Polaritons. But here you have region when you have one kind of interaction when this kind of system, when you have a graphene between this layer, we have interband contribution because the electron could migrate for the same band, for example, in the valence band, or they can give a pull for the other band, the valence band, between the valence band and the conduction band, and we have two kind of contribution for the optical conductivity. Essentially, the optical conductivity will give the behavior of the graphene in this system. If you consider no graphene sheet between this medium, you have the same dispersion relation for the previous case. Okay?
So the graphene, where is the KF that you choose for this picture that you're showing here?
Here?
Yeah.
Here is a cut of the graphene is between this medium. Here we have a flat or a sheet of graphene.
Yeah, but the Fermi level is at the Dirac point.
That's the Fermi level. Okay, the Fermi level here in this figure, of course, you have yes, you have the Fermi level in the Dirac point. If you put the Fermi level in the Dirac point, you have 0, and you have no effect of this optical conductivity. So if you put 0 for this Fermi level, we have 0 here. 0 here, so you have no interference. So you have this kind of behavior in blue here. Okay.
So is there any difference between the P type and the N type when the Fermi level is in the conduction or in the valence band?
Yes.
The plot that you're showing, which one is it?
This picture was is well explained in the book of Nuno Pérez. Here we have a region where when the kind of contribution for the electrons between the inter or interband doesn't matter in this case. Here you have the interband. The region where you have interband is more strongly than interband, and this other region here is when you have the contrary, the interband and the interband here interband here is more strong, and then depend on the kind of approximation you chose. For example, for Kubo, and you have a local Kubo, you have a different kind of behavior. Okay.
Yeah, no, I just wanted to know whether KF is fixed.
Yes, KF is
fixed up there or down here.
It's fixed up there. Is it all right? Okay, sorry. It's up. Let's go. Okay. Of course, that this I will call attention. I forgot to call attention here for this kind of behavior here in that picture. Here we have a book bands, and here you have surface modes. Of course, this surface mode is characterized they appears only after the light line, and then the right side of this picture. And here, of course, if you have a multi-layer system, okay, you have a change of this bookband, and also you have different behavior for the surface mode. Okay. Okay. Here, I will consider a multi-layer system. Okay, it's a photonic crystal essentially. When you have a periodic repetition of A and B layers. A means one kind of semiconductor, and B is other kind of semiconductor, for example, if you want. This structure here, essentially, it will repeat for the infinite, for the right side, and for the left side. But for consider surface mode, you must do a truncation or cut this structure here and consider a semi-infinite medium C generally is a vacuum. Here we call attention for this sigma prime. The sigma prime is the graphene contribution, or represent here the graphene sheet in the first layer. This first layer will play a role for the surface mode, not for the bulk modes, okay? And when you consider this semi-infinite periodic photonic crystals, we will use, as I told for you, I will model the system by this kind of optical conductivity described by a Kuebel formula. The Kuebel formula, we can find this reference. Here we have a contribution for interband and interband, okay? And I will not consider the absorption in this medium, okay? Of course, if you want, we can do this calculation for other regions, but I will consider this approximation for 300 kelvins, and this kind of mu c is related with the level of Fermi level. This is the same Fermi level, okay? Mu c is a chemical potential. Some people call chemical potential, other people call Fermi level, okay? And then in this, we chose this parameter just to give this imaginary part of the conductivity. They have this behavior, and you have almost zero, of course, real part of this optical conductivity. This will give a good improvement, and in other cases we will not have surface mode. If you have the contrary, for example, you have optical conductivity between real part equals to zero, imaginary part like with a behavior like that, and we will not have surface mode. It's important to consider these surface modes, this kind of parameter, just because the graphene is a very, very special kind of materials that you can have this surface mode. This big area now the people call plasmonic, and sometimes you can find a paper just to say plasmons or plasmonic or something like that. They omit the polariton name, but generally I would like to keep this Plasmon-Polaritons mode. Here I will show for you how I can calculate a book-like collective modes or polariton modes when you consider p-polarization. P-polarization is when you have transverse magnetic modes, or the magnetic field is transverse to this section here. This section here that I showed before. I have shown. Okay. Here, the magnetic field is pointed, for example, to outside of this slide. Okay, in this geometry. Consider a plane wave solution, and we have a magnetic field and electric field inside of this multi-layer system, and you can apply the electromagnetic boundary condition. But here we have, for example, a discontinuity for the magnetic field. The magnetic field will be discontinued, just that in this case we consider optical conductivity due to graphene, of course, between that layers. If you get if you use this boundary condition, you can relate the amplitude between a layer n and a layer n plus 1, and you can construct this transfer matrix. Is very know this method, this transfer matrix. And for example, in this approach that I have done, we have cross matrices, and this cross matrices is the cross between the one medium and another. We have contribution for graphene. This is sigma bar. Sigma bar is related to sigma. Sigma is the optical conductivity for graphene. And this is the propagation matrix. And you can have propagation interface, and the interface. But due to the, we can use, for example, the block theorem just to obtain the dispersion relation for the bulk mode. Essentially, you have, we can consider this a half of the trace of matter. 3R means the trace of matter. That matrix here is a 2x2 matrix. Other thing that you can consider here is for the bulk mode, you consider this photonic crystal like an infinite crystal. For surface mode, you should consider truncation here and put the other medium. This medium, for example, is vacuum. Okay? And in this case, we'll keep my attention for the first layer. And in this first layer, we should consider the electrical fields outside of this photonic crystal that it will decay. This is the constant of decay. When we'll show this constant, for example, in my configuration, Z, for minus infinite here, the field should be 0, if you consider this limit. Applying the boundary condition for the first layer, we have this equation, and for the other equations, we must consider a decaying constant. Here is essentially the block theorem, but here we will consider a decayment of this mode. Essentially, you have a decayment of this mode in between these layers here for ensure the localization mode here in the first layer. Okay? If you do some calculation, you can show that this decayment constant is related with your transfer matrices. And of course, here we have a contribution for the optical conductivity of graphene. Here is called sigma prime because here I will give some example if sigma prime is 0 or if sigma prime, or in other words, if we have graphene on the first layer or no graphene on the first layer. Okay? So this is for S polarization. The calculation, originally we don't have S surface mode for S polarization. We have only bulk mode. The literature have many examples for the case. But if you consider graphene, the theory and the calculation show that you have a surface mode for if you consider graphene in this system. Of course, if you not consider graphene, lambda is equals to 0, this equation will not give the right result. Of course, we don't have a surface mode. This is equals 0, 0, and we have these other modes. This equation will not be satisfied. Will not be true. Okay? Our numerical is, I will do now some numerical examples for when you have material that constitute this photonic crystal as a semiconductor. The semiconductor that we chose is gallium arsenide, because gallium arsenide have a very, very good numbers or good level of doping. It's well described in the literature. Okay, this is the reason that you have chose gallium arsenide. You can choose other numbers or other, sorry, not other numbers, or other materials for do this calculation. If you consider gallium arsenide, you must shows the frequency dependence of a direct function like that if you chosen to describe the Plasmon-Polaritons only. If you want to describe, for example, Phonon-Polaritons, the dielectric function or this dependence will change, of course. In this case, we will keep attention only in the region close to the plasma frequency. In this case, this plasma frequency is close to 10 terahertz. Of course, that will have other kind of semiconductor that you can dope in, that you have dop level less than 10 terahertz. Is depend of the system that you want to source this kind of Plasmon-Polaritons. Okay, and here, if you you consider a lower doping level, this is for this frequency. We had calculated this. This is the doping level. For example, the charge density is around this number. If you not consider, for example, this gallium arsenide, not doped gallium arsenide or undoped gallium arsenide, this part is close to 0, and we have essentially a dielectric material. Okay? This numerical example, I will show some pictures that I divided here in 3 cases. The first case, we have all the layers. All layers is, we can consider, for example, in this case, as a dielectric constant. Essentially, we have a graphene sheet, dielectric, and graphene sheet, dielectric, and so on. And then the second example, we have one of these layers as a semiconductor, and the other dielectric medium. And the third example, I have all these layers that compose the photonic crystal as a doped GaAs, or gallium arsenide. Okay? And the first result that I will show you is for p-polarization, and you have p-polarization in the case 1. The case 1, remember, you have all these layers as a dielectric. It's an undoped semiconductor. And here is the case, and you have graphene in the first layer, and so on. When you do this calculation, you have a typical dispersion relation when you have bulk bands limited for the key L equals to 0, key L equals to pi, and L here is the size of the unit cell. Okay, this is my first brilliant zone. Okay, and if you plot the frequency against the wave vector, here is in units, red is in units. Here is this units is related with omega 0 is equals to omega pi, omega p for 9.48 terahertz. Okay, and in all this example, I will consider that the medium B is twice the thickness of the medium B is twice of the medium A. Okay, and here for the so if you consider the first layer here, the first interface, you have a graphene here. We have 1, 2, 3, 4, 5 sulfate modes. The sulfate modes are described here for this black line. Here, we characterize the call vacuum-like line. In other words, is the dispersion relation of the line in vacuum. And this other line, we have a dispersion relation in dielectric medium. The surface mode will lie before this, on the left side in this figure, on the right side, sorry, in the right side of this figure here. All the modes in the right side of this line is a surface mode that you can calculate. To obtain this surface mode, you must keep attention in the decayment constant. Decayment constant is that term here. We show in this picture only the modes when this decayment constant, for example, the inverse of decayment constant is positive or more than 1, just to ensure that beta is real. Okay? And if you keep this in mind, you can find this surface mode. Here you have the two modes. Here is quite different from the case when you have a single interface. But other thing is when you have, for example, 0 close to 0 KUA vector, that means you have a normal incidence, you have a big gap here. Generally, in the literature, they refer this gap like graphene induced gap. Sorry.
So just trying to understand the picture there. So you have a graphene sheet, and whenever you have a dark blue, so it's there.
Yes.
That's one. What about there?
Graphene.
Yeah. And the surface modes you're talking about are the interface modes in each one of these interfaces?
All these interfaces, they will appear here. They will decay here, and this is
yeah. So S1, S2, and S3 are they denoted like the first interface, and the second interface? What is it?
Depend on this surface mode. Depend on the K and omega. Here, if you show the K and omega, you have, for example, here they call S1 just to describe, to call attention here that this mode is close to the band. This will appear close to the band, and this other one is more in this region here. But this S1 and S2 is not related with the number of the layers.
So how do I know where they are if I look?
Okay, this is a good question. Okay, all these modes is that we
and also the graphene layer. Where do you have the chemical potential? Is it in the N type or P type?
We have here. We don't have a semiconductor here. All this layer are dielectric medium.
Yeah, but I mean the graphene layer.
The graphene layer.
Yeah.
We have chose this parameter here, and we don't have absorption. Okay. We have this kind of, let me show you. This is a kind of mode. Have many solutions for this kind of mode. This is just a cartoon, but you can have, for example, in the contrast, here is decayment, but here you have a mode that will decay. The decayment constant is related with the height of this, for example, here in this picture, you have a decayment of this mode in the entire photonic crystal. But answer your question here, sorry. This is the Fermi level that you have chosen. This is
so it's N-type.
Yes, N-type.
You're not considering any bending, right? When you have a graphene, and then on the side you have like gallium arsenide, or but in principle you could have, you know, a flow of charge,
yes, of
and you know, and this is not important, you think?
Yes, of course that is, but you must choose one case, and we choose this very simple case, and you can do for what is important. Okay. Okay, let's go. This is just to call attention. This is these bands that will appear here between the book band. This is the region when you have that book band, if you consider a medium like a semiconductor, and you have the answer for semiconductor like that function that I had showed you. Here, this band will appear if you consider this parameter here, and then if you consider dA is equal to B, dB, for example, the same thickness, this band gap here will disappear. We don't have band gaps here. This is linked with these shows, for example. And here, this band here, this book band here is in this color, very brown color. We have bands related with graphene. If you have no graphene, for example, this band gap here will disappear. We have just one bulk band and the forbidden region, and the other region you have surface mode. But with graphene, you have this kind of they call induced band gap. In all the figures, you will see this band here. For example, if you have graphene for p polarization, just for p polarization, you have S polarization. We don't have this kind of band gap. When you consider more higher wave vector, this band gap will join together. And for example, in the infinite, we have only two kind of. Here is a mix of bands, the book bands and surface mode. But if you make a zoom here, you can see the difference between. And here you have one surface mode for K when K goes to infinite, for example. This is for P polarization when you have no graphene sheet in this first surface. Observe when the dispersion relation will change. It is strongly dependent of the first layer. Of course, these other modes, we have a localization here, but they will decay in different forms because we have only two surface modes. We have two kind of interface, AB and CB here. Is just the reason you have these two surface modes. A and B, if you have no change, or if you have no difference between A and B, for example, in the thickness, we have only one surface mode. Okay? And so, for P polarization, practically you have no surface mode. In the P polarization, S polarization, you have no surface mode practically. This mode will appear very close to the band. Probably I put here just for completeness, but for experimental, for example, it's difficult to measure this kind of behavior when they have a surface mode very close to the band. But mathematically it exists, but I don't know if the people will detect in some experimental setup. This is the case when you have one, for example, a layer A for the photonic crystal are intrinsic gallium arsenide or doped gallium arsenide. Here and layers B are here is undoped. A is undoped and B is doped gallium arsenide. We have one. This is I think that is a kind of the answer for your question. You have, for example, you have doped and undoped. You have a distribution of the different bands in the photonic equation. For the graphene, is the same. Yes, we assume for the same. But when we have a semiconductor here, the potential will up here in that case. This is a different case for the other one where I showed you. Here we have the zero, for example, for this zero energy firm or potential chemical potential, and here you have a different chemical potential, and so on. And here, other important rule is here to have a chemical potential for a small chemical potential for the graphene between the layers. Okay? Because here in each interface you have a graphene sheet. Okay? And so, if you calculate the p-polarization, Plasmon-Polaritons dispersion relation for p-polarization in this system, we have a lot of surface mode that is allowed to propagate. It's a very, very interesting case when you have one medium with that is a doped semiconductor and the other is an intrinsic semiconductor. Okay? And here, particularly this band that in other cases is very, very clear here, is started to disappear. Here is for when you don't have graphene in the first layer. In this case, we have just one surface mode. Just one surface mode. So if you don't consider graphene in the first layer. And the book band is the same, okay, but the graphene, the surface modes will, the other surface mode will disappear. Sorry. For S polarization, if you consider S polarization, you have no surface mode in this case. Remember, in this case, you have one layer is an intrinsic semiconductor, and the other is a doped semiconductor. Okay. In this case, we have no surface mode. Generally, in this case that the people, if you talk with the guy that work with this kind of system, that will say, oh, don't have as surface mode for S polarization. Just to have a book band. But not that the book band is different for S polarization than P polarization. Okay? You have a different behavior in these book bands. It's like a parabola. Exactly when I showed that picture in the beginning of my talk. And this other result is just for when you have all these layers, all these layers are a doped semiconductor or doped gallium arsenide. If you consider all the equation, all this medium as a doped gallium arsenide, we have this kind of behavior here. Of course, these book bands, this behavior of book band is due to all the system is a big semiconductor. And this branch here is exactly due to have a graphene sheet between these layers. Okay? And if you make a zoom in that region in blue here, we have a kind of behavior in when you have a mix of semiconductor and intrinsic semiconductor and doped semiconductor in the other case. But the difference here that you have the graphene-induced band gap for the graphene. It will appear up the plasmon frequency. Below the plasmon frequency, we don't have surface mode. And here we have this kind of main kind of surface modes here that will appear between the book bands, and here that someone that is very close to the book bands. This kind of surface mode again is difficult to measure for to detect experimentally, and we keep attention only in this case. If you put now sigma, the first layer, so if you consider no graphene in the first layer, you have this kind of dispersion relation. Just one surface mode is allowed to propagate here in the interface between the first and the photonic crystals. Okay? So if you have S polarization, certainly it was a surprise to find this kind of mode here. We hope don't find this kind of surface mode, but here it is very, very clear and between the bands and below the band. And this is a very interesting case. And I will stop here. Of course, that have more result that I work on my collaboration with Professor Mike Cotton, but I don't have time to do this. For example, we consider this same system when we apply a magnetic field. It's a very interesting problem that we send this paper for journal. We're waiting for answer. Here's the conclusion of this talk. If we have studied the special relation for Plasmon-Polaritons corresponding to 3 different arrangements, all the layers are intrinsic, undoped gallium arsenide. And the second case, when they have a layer A and B, alternate intrinsic gallium arsenide and doped GAS. All these layers are doped GAS. We stress here that when you compare all these cases, we find that the inclusion of the doped semiconductor medium in photonic crystal will affect the dispersion rates, mainly at low frequency. When I have pointed for you, and I had pointed for you here, is just to say that when you have doping semiconductor layers, we have like a parabolic, the dispersion relation like a parabolic behavior will keep if you consider that case. Also, and the special relation for book, we have many band gaps that will appear, and in different cases, S and P polarization, you have the very, very clear difference, and in the book bands, it's not like, for example, if you study Plasmon-Polaritons in semiconductor, then when you have and A and B, or N and P, or NIPI, and this kind of thing, you have a very you don't have surface modes in the S polarization, but here we found one case when we have one configuration, we have surface mode for S polarization, but for graphene sheet between the layers. Graphene sheet between the layers of this photon crystal. Particularly, we have studied the effect of this graphene sheet in the first layer. If you have graphene sheet in the first layer, or you have no graphene in the first layer, you have a big difference in your surface mode. This is a very interesting effect if you, for example, if you want to construct a kind of this device or optical electron device. These results show in general that we can have more surface molding dispersion relation when you consider that this graphene sheet in the first layer. Okay? Some acknowledgement. This is the people that pay for me to this work. This is some collaboration. This is Professor Mike Cotton in the Department of Physics and Astronomy, University of Western Ontario. And in Canada, this is other guys, some other collaborators that there's some guy that we have collaborated in past 5 years. And I have other guy here. This is other guy that we work in other kind of system, quasi-period system. This is my PhD students, Allison and Everson, and thank you very much.
Do we have any further questions?
So I'm going to go back to my previous question about the chemical potential and whether you actually solve Poisson's equation